Hello friends, this is the first part of a series of videos introducing Bash programmers to Go. This part goes through the language building blocks that will be used in later parts. There is also a text version of this video which I will link in the description. The link contains also most of the code I will be mentioning. So if you prefer the text version and you want to see the code repository, click the link below. Bash code is stored in scripts, which are just text files. So for example, I create this hello sh file, enter the interpreter, the Bash interpreter for my program, and write my program, echo hello. Then I change the file to be executable, and I just simply run it. For Go programs, they are also stored in files, so let's create a Go file. Each Go program is composed of one or more packages. If you want the program to be executable as opposed to an importable library, you need to have the main package, and inside the main package you need to have the main function, which is the entry point for the program. This is the place where the execution of your Go program starts. So let's use the built-in FMT package, a package from Go's standard library that has a print line function, and we print our hello string. When I save the program, it will automatically import the package for me, and now I can run it like this: go run hello Go, and spread a Go package code into multiple files, but the files need to be in the same directory. So for example, let's create a new file called greeting.go. It will be part of the package main, the same package as for the hello.go file, and we'll define a constant called greeting that has a value of hello. Now we go to the original file, and we can use the constant here. To run the code, we need to include both files, so hello.go and greeting.go. A compiled programming language, it means that you compile the Go code into a binary and then you run the binary. So you might be wondering what this go run command is doing. If you look at the help, we can see that go run command compiles and runs the Go code. So it builds the code in some temporary folder and then runs it. So what it basically does is something like go build hello.go greeting.go. Now we have built a binary called hello, and we run the binary. But what's really cool is that we can build Go code into binaries for virtually any operating system and any CPU architecture. For example, I have a Raspberry Pi based Linux server at home. So I log in to this server and I check the operating system and architecture. So the operating system is Linux and the architecture is, the CPU architecture is ARM64. Okay, I disconnect from the server and now we can try to build our Go code for my Raspberry Pi Linux server, although I'm on a Mac right now. So there is a tool, go tool dist list. There is this command that lists all the supported operating systems and CPU architectures. I know that I'm interested in Linux, so I grab for Linux. And I said my home server is a ARM64 CPU architecture. So to build for this operating system, we just set the environment variable called GoOS and another environment variable called GoArch we set to ARM64. And now we build the binary as usual, hello.go, greeting.go. Now we have a resulting binary, hello, that we can't run on Mac because it's meant to be run on Linux, ARM64 CPU. But if I copy this binary to my server, and run it on my server, it works. This last command is basically the same thing as SSHing to the server and running it there. About variables and types. So in Bash, we can define variables like this: name equals Jack, age equals 40, active equals true, and we don't really care about the variable type. So for example, the variable age looks like variable for holding an integer, but we can reassign a string into this variable, and this is not a problem for Bash. So if we run this, there is no problem. In Go, each variable has to have a type. So for example, I define a variable age and I need to set a type for it. Let's say it's an integer, and it can hold only integer values. So if I try to reassign a string into this variable, I get a compile time error. Cannot use 40, which is a string, as an int value in assignment, line 5, column 8. We had another error there saying that we defined age variable, but we have never used it. So if I do like, if I just print it, I get rid of the first error, but I still have the type error. We sometimes need to convert variable types, and the conversion is done like this. So for example, we have a variable of type string, by the way, this is another way how to declare and initialize a variable using this colon equal, and this is a shortcut for this. So we leave out var and we leave out string. This is handled by the colon basically, and the type of the variable is inferred from the right side. But let's say we need to convert the type of the name variable into byte slice. We'll talk about slices later. Now the important thing is the conversion, or sometimes called casting. So name bytes, this is a new variable, and we convert the name variable, which is of type string, into slice of byte like this. Now if we print out the type of the variable, we'll see that it's no longer string variable, but slice of bytes variable. Byte is a alias for unsigned integer of 8 bits. However, it's not always possible to convert a type in this fashion. For example, let's say we have an age variable which is of type string, and we want to convert it into int. So we might be tempted to do something like this. But we can see that this doesn't work, cannot convert age, which is variable of type string, to type int. In this case, we need to use a standard library package and a function a to I, like ASCII to integer, that takes a string as an argument and returns an integer and a potential error. So we supply h as an argument, we take the resulting string, and we ignore the error for now, for simplicity. We'll talk about errors later. Now we can print the type and the value of the I variable. So we can see that now it's an integer and the value is 40, an integer. If you declare a variable without an explicit value, for example, like this, the variable is given its 0 value. For integers, it's 0. For floats, it's 0. For booleans, it's false, and for strings, it's empty string. We can verify it like this. So we print the values of all variables. BS. Let's run this. 0 for integers, 0 for floats, false for booleans, and empty string for strings. Another thing to mention about variables is that they have a scope. All these variables defined within function are function scoped. It means they are visible within curly braces of the function. If I would define a variable here, this variable would be package scoped, so this I variable would be visible within the whole main package, and within the main function it would be overshadowed by this variable I. And the third scope is a statement scope. So for example, if I create a range loop, some slice, this I variable would be visible only within the braces of this for statement. So to repeat, there are 3 scopes for variables: statement scope, function scope, and package scope. Go's type system and scoping rules prevent many common errors that can occur in interpreted languages like Bash, Python, Perl, especially as they grow larger and more complex and are maintained over time. These are some of the most commonly used basic types, but except for these basic types, there are also aggregate types that can hold multiple pieces of data. Now I'm going to talk about 2 of them. First are called slices, and I will show you basic operations on slices. So let's define a slice called primes. It will be a slice of integers, and let's initialize it with some values: 2, 3, 5, 7, 11. Now, a common operation is to append an element. Primes append primes 13. So we append another element, number 13, into the slice primes, but the append operator returns the slice with the appended element, so we need to reassign it. Another common operation is accessing some elements. So, for example, let's say we want to print the first element, which is at index 0, and the last element, which is at index the length of the slice -1. We can even slice a slice, so we can assign a part of the slice to another slice. So let's say we want to take the number 3, 5, and 7, which is the second till fourth element excluded. So now the slice will contain these 3 elements, and we might want to loop over all slice elements. So we do it like this. We print all the slides, all the elements of the slice. We are missing the range operator. And there is another problem. Line 8. We are missing a parenthesis here. Okay, so here we range through all elements of primes slice. We ignore the index, we are just interested in the values of the elements. Another non-basic type is called a map. You might know it from other languages under the name associative array, dictionary, or a hash. And the map maps keys to values. So let's go through some common operations on maps. First, we create a map of string to integers, and let's initialize the map with some values. So the key is 1, and we map it to value 1, integer. Next, let's map string 2 to integer 2 and string 3 to integer 3. So here we declared and initialized a map. Now we might want to insert another element with the key 4 and the value 4, or we might want to retrieve some element. Let's say we want the value of element at key 1. LM will contain the integer 1. We might even want to delete some elements. So let's say we delete element from map M at key 4. So we removed element we added here. And there is also like two value assignment, which is useful for discovering whether we receive a real value or the zero value for the type from the map. So in this case, the lm equals 2, because at the key 2 there is the value 2, and OK is true. But if we ask for an element that is not in the map, we will receive the zero value for the given type, which is 0 for integers, and the OK will be false. We might also want to range through all the elements with the range operator, and for each iteration we will have the key and value of one of the elements. The order of the elements is undefined. So be careful. The order of the elements printed in the for range loop won't be the same as here. Might be, but it's not guaranteed. Most languages have multiple statements for looping, like for loop, while loop, do, while loop. But in Go, there is only for loop, although it can implement the functionality of all the loop types. Let's see some common examples. So we have the traditional C style loop like this. So we initialize the variable I to 0. We loop until the condition I is less than 10 is true. And on each iteration we increment the variable I by 1. So we can print the variable I, and when we run it, we get 0, 1, 2, 3, 4, 5, 6, 8, 9. Then we have we can have a while loop. So while I is less than 10, print something. I is less than 10. Increment I by 1. But first we need to initialize I. So we can do it like this. In this case, I is initialized to 0 because that's the 0 value for integers. Or we could do also something like this. So this is a while loop, and we can also have a infinite loop, which is very simple. It's like this. So this loop will run forever. Infinity and beyond, right? We had time, we had a sleep here for a second, so we don't get the output too quickly. So that's the infinite loop. Sometimes you might want to break out of a loop. So for example, you might have a construct like this. So you have an infinite loop. There is some function that does something, but if there is an error, if the function returns an error, we break out of the loop, of this loop. Otherwise we keep doing something. Or you might want to use the continue statement. For example, you go through numbers from 0 to 9, and if the number is even, you continue. It means you restart the loop. If the number is odd, you print something. Let's talk about functions now. So up until now we've been using only one function, the main function, which is the program's entry point. But we can have our own functions. This is similar in Bash, but the functions in Go are much more powerful. So let's have a look. We'll define a function named greet, which takes parameter named who of type string and returns a string. And what the function does, it returns a string that looks like this. Hello. Oh. By the way, if you want to see these verbs, see what verbs are available for formatting and what they do, you can go to go doc fmt sprint. Now go doc fmt, and the verbs are described here at the top. Or you can visit the web page, online documentation. Okay, so this is the function. We call a function like this. Since it returns a value, we store the value in a variable, and we can print the variable. Functions in Go can even have multiple arguments and can return multiple values. So here, for example, we have a function called divide that takes two arguments of type int and returns two values, int and error. So let's see how we call a function like this. So we have a function name, argument 1, argument 2, and we have two return values. Let's say result and error. We first check whether there was an error. If there was, we print the error to standard error and exit If there was no error, we print the result. So let's test it. What was it saying? Cannot use error variable type interface type error as string value in error and f print line 12. Line 12. All right, so okay, so we have the error message, division by 0. If we change the parameter, we get the result. So in the first case, we were here. In the second case, we were here. Now let's talk about the dreaded subject, pointers. But pointers are not that difficult. They are just not being used in interpreted languages like Bash, Python, Perl. So people are not that used to them. If we define a variable like an integer type variable, this variable actually is an alias for a memory address. What is the actual memory address? In Go, we can get it by prefixing the variable name with the @ symbol. And if we want to have a look, we just print it. So you see, this is the address of a place in memory where the value of variable I is stored. And we get to this address by using the @ operator, and this address is called a pointer. We can store the pointer into another variable, and this variable is a pointer to the memory address of this variable. So now, again, if we print this pointer, we get this huge number, this large number. But if we want to get to the number, to the value that is stored at this memory address, we need to dereference the pointer, and we use the star operator for this. So this is the memory address, and this is the value at the memory address. Again, the name of the variable I is just an alias for this memory address because it's easier to remember. Okay, now where are pointers, or why are pointers useful? So the main use case is if we have a function like let's call it inc, that takes an integer as a parameter, and it increases this parameter by 1. So now you might expect that what will be printed will be number 2. Let's test. It's still 1. Why is that? The reason is that this, or better, this is a copy of this value. So this is a different variable that's holding this value. If we want to mutate this variable, we need to take a pointer like this, and here we need to add sign, and now we should be good. Okay. Okay, now we get 2. So just to explain, so we pass a pointer to I variable here. We dereference the pointer here, so we get to the value and we increment the value. That's why now when we print the value from the I variable, we get 2. Next topic is structs and methods. Bash does not have support for structs or methods. The closest you can get is using associative arrays. So you can, in Bash you can group data like here, like this. So define the person associative array, and you do person name value Alice and person age value 30. To access the fields, you do something like this. But as you can see, it's somehow ugly, and it's not used much in Bash. In Go, we can create our own types based on structs. So for example, let's create a type called person, which is based on struct type. And struct type is basically an aggregate data type that can have 0 or more fields, and the fields can be of different types. So let's put in 2 fields, name, which is of type string, and age of type integer. Now, how do we create a variable of this type? It's easy. We create it like this. Person, let's say the name is Alice and the age is 30. If we want to print the fields, we do it like this. So the name field is p.name and the age field is p.age. Okay. Age is an integer. All right. Now, we can attach behavior to types in Go. This is kind of a object-oriented programming. How do we attach behavior? So we create a normal function. Let's say we call it greet, and we prefix the function with the type. This thing is called a receiver. It's similar to function parameter. And now inside the function we can access the data from the type. Hello, my name is name and I'm some age. P name, P age. Okay. Now we can call functions on this type. So P greet, person greet. Let's test. Hello, my name is Alice and I'm 30. Okay. Let's define another function. Increment or inc age, increment age by some number of years, and we attach it to the person type. But what we have shown before about the function parameters, we said that they are copied. They are copies of the values passed into the function. The same is true about the receiver. So if we want to mutate the value, we need to use a pointer. Okay, so now we can increase the age by years. We can increment the age of the person by years. We don't need to dereference the value in this case like this. This is not needed. This is automatically done by Go, because it's nicer on the eyes. So let's try it. Increase age by 10. So here Alice is 30, but here she should be 40. Let's test. Yeah, she's 40. Now we'll talk about interfaces. When I first heard about the interfaces, they were very alien to me. So you need to get used to them. There are no interfaces in Bash. And in Go, an interface is an abstract type that describes some behavior by using a set of function signatures. What does it mean? Let's have a look at an interface in the Go standard library. For example, the FNT stringer interface. So this interface is defined in the standard library FNT package, and it looks like this. So it's a type named stringer, and it's an interface. So as I said, interface is kind of a meta type because it doesn't hold any data. It just defines some behavior. And this behavior can be implemented by any type that has this method attached. So let's see an example. Let's say we have a type named backup, which is a struct, and it has 3 fields: description, which is string, size in 64, this will be bytes, size in bytes, and last done, this will be time. Okay. Now let's use this type. We say description, personal code, size 1024, and last done now. Okay. Now if we print this type like this, we get some output. It's kind of readable, but it's not that nice. When we have a look at the stringer interface again, we see that the string method of the stringer is used to print values passed as an operand to any format that accepts a string, or to an unformatted printer such as print. So let's try to implement this interface. So let's turn the backup type to a stringer by attaching a method to it with this signature. We need to attach it to backup. And basically, now we have turned our custom type called backup into a stringer, because it has this string method. So now when we call the print function on it, this method should be called and its output will be printed by print line. Let's see. Yes, we haven't implemented this function. So first, let's try empty string. Yeah, and we can see it works because it has returned the empty string. Let's put in something more useful. So let's say something like backup of this, which contains these bytes, was last done on this date. Now we enter data, description, backup size, and backup last done. Let's see now. Okay, now it looks pretty good. Backup of personal code. 1024 bytes was last down this date and time. We could play a little bit more with this, but that's the main idea. Another standard library interface is called IO Writer, and it looks like this, and it's used in many places in the standard library. For example, fnt fprint function takes IO Writer as the first argument. There are also many implementations of IO Writer in the standard library. For example, the OS standard error type implements IO Writer. How do I know? It's together with standard out and standard in, it's a file because it's created by a new file function. And if we look at the file type, we see that it has many methods attached, including the write method with the signature of IO Writer. So this method has the same signature as is required by the writer interface. So it means that the file type implements the writer, the IO Writer. So how is this useful? Okay, so we said that fprint takes IO Writer as the first argument. This way we can print to standard error, we can use the same function to print to standard out, and we can use the same function to print to network connections. So we create a TCP network connection to this host and port. This function returns netcom and a potential error. We check the error. If it's not nil, we exit with the error. Otherwise, we can start printing stuff to the network connection. Okay, so how does this work? So again, if you look at this netdial function, you see that it returns con type. Let's have a look at the con type. Go doc net con. So this is again an interface. Which has the write method. That means that it implements the IO Writer, and that's the reason why we can use it as a parameter to fprint. Okay, let's have some fun now, since we are getting tired and it's getting dark here, as you can see by the change of the color in my terminal. We'll craft a package that will have a function telling us whether a word is a palindrome. A palindrome is a word or a string that reads the same forward and backwards. Let's create a directory called word and a subdirectory for our first attempt, our version 1. And we'll create word.go. This time it will not be a package main, but package word. And we create this function. Func is palindrome. It takes in a string and returns a bool. Let's add some comment. Is palindrome reports whether S reads the same forward and backward. Alright, so now how to do this? What about arranging over the string elements and taking the elements index and comparing the edge elements so here on the first iteration over the string elements I will be 0, so we will try to compare the element at index 0, which is the first element, with the element at index length of the string slice -1. I is 0, so it's nothing. So we will compare the first element with the last element. If they are not equal, we know it's not a palindrome. Otherwise we keep looping, and in the second iteration we compare the second element with the second to last element, and so on. If all the elements are the same, we have a palindrome and we return true. Okay. Now this function looks good, but in the words of John Osterhout from his book A Philosophy of Software Design, we should do strategic programming instead of tactical programming. It means that we should spend more effort in advance to save effort long term. Because of this, let's create some test. Okay. So how we do testing in Go? We must create a function that starts with test and then some description. We can use the function name. And we import the testing package like this. And now we call our function is palindrome. We supply it a string that we know is a palindrome, and if the function returns false, we know there is some problem, so we report this problem. Okay, we provide some informative output. We need to use back quotes here because we used quotes inside the string. Okay, and we run the test like this: go test. We haven't created a module, so let's create a module so the Go tooling works smoothly. Go mod init. It should be something like github.com go monk /word, but for our purposes let's keep it short. Now we run the test and we see that it has passed. Cool. Life is good. We drink coffee, we read books, but suddenly a Slack message pops up and one of our colleagues from Slovakia is complaining about the new package, the board package, and he says that the function is palindrome doesn't recognize the word ťahať as a palindrome. Really? We think to ourselves, let's find out. So we create a version 2 of our package, and we turn this complaint into a test case. Okay, let's see. Oh, really? So this definitely looks like a palindrome, but our function reports it's not a palindrome. What's going on here? After a bit of, or quite a lot of research, we find out by reading this URL or the document at this URL how strings really work in Go. We find out that strings are just sequences of bytes, of any bytes, and a string is not required to hold Unicode text, UTF-8 text, or any other predefined format. That means that we need to turn this string, which is just a slice of bytes, into runes. And we do it like this. We convert string into slice of runes, and now we range over the runes, and this might have fixed our problem. Let's see. Okay, there is some error on line 7. Cool. Now the tests pass again. It didn't take long, and we've got another bug report. This time, some smartass came up with this cool sentence. Okay. Our current implementation doesn't recognize this sentence as a palindrome. So let's work on a new version. But first, let's improve our tests. We'll take an approach called table-driven testing. So first let's define a slice of structs, and each struct will hold some input, which is the string, and whether this string is a palindrome or not. Okay, let's reiterate our existing tests. So kayak is definitely a palindrome. We also know that the word cat is a palindrome, and also this string is a palindrome. Let's throw in some edge cases. This is a palindrome also, and this is not a palindrome. Okay, now we range over the tests and call is palindrome for each test. Take the function output and compare it with what the output is supposed to be, what we want. If it doesn't match, we report an error. Let's test our test. Line 6, declared or not used. Okay, this is supposed to be tests. Line 18, we want to use error F. Okay. So, as expected, we are failing on this string. So, what is the problem? The problem is that we are not ignoring white spaces, we are not ignoring punctuation, and we are not ignoring uppercase letters. Let's fix this. Okay. So let's create a new slice of runes called letters that will hold only letters. We range over the string, and if the string is a Unicode letter, this is a standard library package. If the element of the string is a Unicode letter, we append it to the letters. Making it lowercase. By the way, this for range loop iterates over runes, not over bytes. Okay, so in letters we have only UTF-8 letters. Rune is a UTF-8 call point or letter, let's say. So now we can iterate over the letters and do the same as before. So let's see. Cool. Our last topic is concurrency, Goroutines, and channels. Concurrency is a way of structuring a program such that multiple functions can execute non-sequentially. If there are multiple CPUs on the machine where you are running your code, which is very likely today, they get executed in parallel. Goroutines and channels are, for some people, one of the most interesting features of Go, since they make concurrent programming relatively easy. Nevertheless, concurrent programming is still inherently more complex for our brains than sequential, so you should use concurrency only when it really makes sense. Let's have a look. So here we have a function called fib that calculates nth Fibonacci number. It's a recursive function because it calls itself. It calls itself repeatedly until this condition becomes true, and then it returns. Each recursive function has to have a condition like this, otherwise it would keep calling itself forever and the program would crash with Stack Overflow error. So if we run this code, we see it takes some time, but then it calculates the number. It's kind of slow because the algorithm, the recursive function is a slow algorithm for calculating Fibonacci numbers, but I use it to demonstrate concurrency. So it would be nice to see some notification, some progress bar while the program is running. And we have such thing here. We created this spinner function that has a parameter delay that defines the speed of the rotation of the spinner. But now we have a problem, because if we call the spinner with let's say 100 millisecond delay, if we call the spinner before the flip function, let's see what happens. So the spinner is working nicely, but it would spin forever until I interrupt the program. And this is because the Fibonacci, the flip function, will start executing only after the spinner function exits or returns, and the spinner function never returns because it's running in a for loop. So what to do? We have this Go keyword in Go that is similar to @ in Bash, and this Go keyword means that the statement completes immediately and executes on a new, the function executes on a new Goroutine, and the next function can start executing on the main Goroutine. So let's see how does it work. Yes, this works as expected, except for the fact that we forget to print out the result. So let's do it like this. So the program is running, and here is the result. Okay, this is nice, but notice that once we run the spinner function in a new Goroutine, we have no way to communicate with it or even stop it. It works in this case because the spinner writes stuff to the terminal to the standard output, and it gets stopped when the whole program terminates after calculating and printing the Fibonacci number. But in case we want to read output from some function that's executing on an independent Goroutine, or we want to coordinate its execution, like stopping it and starting it, we need to use channels. Channels are similar to shell pipes, but are typed, must be of certain type. This is how we declare a channel. In this case, it's of type integer. This is how we send on a channel. And this is how we receive or read from a channel. Now let's have a look at a example. So here we have a fib function again, but this time it doesn't calculate nth number, but it keeps sending numbers from the Fibonacci sequence on a channel. This is the return value of the fib function. It's a channel of integer. It's a read-only channel of integers, so we can only receive from this channel. How is the function implemented? So first we declare and initialize the channel, or we create the channel. Then on a Goroutine we run a function that keeps producing Fibonacci numbers, and it keeps sending the numbers on the channel. This Goroutine is executed independently, so we can continue here and we return the channel which is used inside the function, inside the Goroutine. In the main function, we call the fib function, get the channel, and then we do 46 iteration, meaning we call or we receive from the channel 46 Fibonacci numbers. I put the sleep here so we can better see that we are actually controlling the execution of this function via this loop. The reason is that this channel can hold only one element, and until this one element is not read from the channel, it cannot send new element on the channel. So when it sends one number to the channel C here, we have to receive the number here. Only then it can send a new number. So let's see this in action. And that's it. Thank you for watching. Bye bye.